Hi, everyone, and welcome to the lecture on acid-base chemistry, buffers, and pH. Lots and lots of chemical reactions occur in aqueous solutions, and therefore water is a very important component of acid-base chemistry as well as some other chemistry. Water is highly polar, as you know, because of its bent geometry that you learned about when we were studying VSEPR. Water is very highly cohesive because of intermolecular forces called hydrogen bonding. These intermolecular forces are not covalent or ionic bonds. They're not that strong. They're weaker, and they are attractive forces between molecules, not between atoms like a covalent bond or between ions like an ionic bond would be. But they're additive even though they're weak. And so if there's a lot of these hydrogen bonds, then you can have a very strong attraction. Water molecules participate in hydrogen bonding with other water molecules and also with biomolecules, such as proteins. These cohesive forces from intermolecular hydrogen bonding attractions allow water to participate with one another in a very strong interaction that holds those particles together. This is the type of interaction that assists surface tension that you've learned about. As you know from talking about polarity, water has an oxygen with a partial negative charge and two hydrogens with partial positive charges. When you put a lot of water molecules together, these partial positive and partial negative charges on adjacent molecules attract one another. And so if we look at two adjacent molecules, we see here that this oxygen with a partial negative charge has an attractive force with this hydrogen that has a partial positive charge. That occurs with most all the molecules that are in a similar proximity to one another. So here you can see another partial negatively charged oxygen being attracted to a partially positively charged hydrogen on an adjacent molecule. And here you can see a partial positive charge on this hydrogen being attracted to a partial negative charge on this oxygen, and another water molecule here with a partial positive charge getting involved. So this results in very strong or highly cohesive forces associated with water molecules. It's important to understand some of these processes associated with water molecules because the first theory we're going to talk about in acid-base chemistry is the Arrhenius theory. Arrhenius determined that acid-base chemistry takes place in water, and therefore an acid and a base should be defined by its reaction with water. Arrhenius said an acid is a species that contains a hydrogen ion, an H+, that is released into water. And so HCl, gas, hydrogen chloride gas, for example, in water will react to release H+, hydrogen ion, and chloride ion. An Arrhenius base is derived from a hydroxide containing compound that releases OH- or hydroxide into water. So if we had sodium hydroxide, for example, reacting in water, we would release Na+ and OH-. Now, according to Arrhenius, what's important here is that you understand the H+ released in water is what makes a solution acidic, and the OH- released in solution is what makes a solution basic. Bronsted-Lowry are two scientists who were doing research on acid-base chemistry as well and derived a theory. And their theory went beyond having a base that's composed of a compound containing hydroxide, so that other bases could be incorporated into the acid-base theory. Their idea of a proton is released from a compound that contains hydrogen, but that proton is donated in this solution. And Bronsted-Lowry's idea of a base also involves a proton. So their theory states that a base is a proton acceptor in solution. These terms proton and hydrogen ion are used equivalently, and also hydronium ion is used equivalently to proton or hydrogen ion. Hydrogen, as it is a proton and an electron. So if you have a hydrogen atom that loses an electron, the only thing that's left is H+, or a proton. In aqueous solutions, hydrogen ions, H+, react with water and they form hydronium ions. And so that's why we're saying that the proton, the hydrogen ion, and the hydronium ion are all the same species in acid-base chemistry. And if we refer to a proton, we're referring to a hydrogen ion. If we refer to either one of those two, we're referring to hydronium ion, because we all know that H+ is not very stable. And in an aqueous solution, it's going to react with H2O, and it's going to form hydronium ion, H3O+. The other thing you need to realize is that when we're writing chemical reactions and chemical formulas, we'd rather write H+ than H3O+, because it's shorter. The Bronsted-Lowry acid-base reaction, or one Bronsted-Lowry acid-base reaction, can look like the one at the bottom of the screen, where sodium hydroxide is reacting with hydrogen chloride gas to form aqueous H2O and aqueous NaCl. I want to make a change right here, because this wouldn't be aqueous. If we have water, we call it liquid. So we have sodium hydroxide base, that is our OH minus and our Na+ species here. And we have HCl, that is H+, and Cl- species here. So what happens is the OH minus is going to accept a proton from HCl. How do we know that happens? Because OH minus becomes H2O in the products by accepting that proton from HCl. HCl, by donating this proton, becomes Cl-, and the sodium that used to be bonded to the OH is now going to be hanging around with that Cl- in the products. You might recognize this reaction as a double displacement or a double replacement reaction, which it is. Both of our cations switch partners. So the sodium now has chloride for a partner, and the hydrogen now has OH- for a partner. In fact, you know that water is HOH, or H2O. Bronsted-Lowry also determined that we have conjugate acid-base pairs. That means that we have an acid and a base that work like partners in an acid-base reaction. And chemically, they look very similar, but they differ only by one hydrogen and the charge that's associated with a proton. So they differ by an H+. If we look at this first reaction here with hydrofluoric acid and water, forming hydronium ion and fluoride ion, and we focus on the forward reaction. And so that's what we have here. We focus on this forward reaction, we can see that HF becomes F- in the product. That means that HF donated a proton, because the fluoride in the products has one less hydrogen and is more negatively charged by 1. If we look at H2O, we can see that H2O accepted that proton that hydrofluoric acid donated, because in the products, H2O becomes H3O+. Notice that H3O plus has one more proton and is more positively charged by 1 compared to H2O. HF is a proton donor, meaning HF is an acid. And H2O is a proton acceptor, meaning H2O is a base. Now let's have a look at the reverse reaction. In other words, we're going to call our products, our original products, reactants, and our original reactants become products when we look at the reverse reaction, and that is here. So H3O plus in the reactants now becomes H2O in the products. In other words, H2O has one less proton and is more negatively charged by 1. If we look at F minus becomes HF in the products. That is, that F minus has one less proton and is more negatively charged by 1 compared to HF. Now let's look at the bottom of the screen here. And you can see that HF and F minus are conjugate pairs. H2O and H3O plus are also conjugate pairs. Let's think about the differences between the acids and the bases here. And so again, an acid, according to Bronsted-Lowry, is a proton donor, and a base is a proton acceptor. So HF has a proton in the reactants, and we see it gave that proton up when we get to the products. So HF, in other words, is a Bronsted-Lowry acid. While F minus is a Bronsted-Lowry base. H2O, on the other hand, is going to accept a proton, and that's the definition of a Bronsted-Lowry base. While H3O plus will donate a proton to solution, and that's the definition of a Bronsted-Lowry acid. You can see in acid-base reactions, we start out with an acid and a base, and we form the conjugates of that acid and base. This is the way acid-base chemistry, for this class at least, is always going to look. Whatever acid and base we start with, the products will be the conjugates of that acid and base. So you should always be able to write the products out for an acid-base reaction. We have a convention for how we write acid-base chemistry when we're just looking at the acid and its conjugate base. So we write the acid first, and then a slash line, and then the conjugate base. So HF slash F minus, the acid and its conjugate base. And notice the conjugate base has one less proton and is more negatively charged by 1. If we look at H3O plus and its conjugate base, H2O, notice that H2O has one less proton and is more negatively charged by 1. So if we look at this definition right here of the conjugate base, one fewer hydrogen atoms than the acid and more negative charge than the acid by 1, because when we talk about the hydrogen atom, we're really talking about H plus. If we look at this other definition at the bottom of the screen for a conjugate base, the species remaining after a proton is removed from a Bronsted-Lowry acid. So for example, suppose we have HF and we remove an H plus. What we are left with when we remove the H plus is F minus. That's our conjugate base. If we look at the definition up top here about an acid, one more hydrogen atom than the base and less negative charge than the base. So let's look at H3O plus and H2O. H3O plus has one more hydrogen atom than the base and less negative charge than the base. H2O is neutral. H3O has a +1 charge, so that means it has less negative charge compared to the base. If we look at this definition of a conjugate acid, it's the species formed when a proton is added to a Bronsted-Lowry base. So if we look at F- as our Bronsted-Lowry base, and we add a proton to that, then we have HF. We added an H plus. The positive and negative charges neutralized each other, and so we end up with HF as a neutral compound, hydrofluoric acid. Amphiprotic or amphoteric substances can act like either an acid or a base. They can either lose or accept a proton according to the Bronsted-Lowry theory of acid-base chemistry. If we look at this first equation, we see that nitric acid is reacting with water to form hydronium ion and nitrate. Now the nitric acid will form its conjugate in the products. And notice that what happened is the nitric acid formed nitrate in the products, lost or donated this proton right here. And so nitrate has one less proton and is more negatively charged by 1. That's an acid conjugate base pair. If nitric acid is behaving like the acid and donating its proton, that means that water is behaving like a base and accepting a proton. And when we evaluate what's happening from reactant to product, we see that H2O becomes H3O plus, and therefore accepted a proton and indeed is behaving like a base. Let's have a look at the reaction at the bottom of the screen with ammonia in water to form ammonium ion and hydroxide ion. The ammonia in this case, if we look at reactants to products, the ammonia goes from NH3 to NH4 plus. In other words, is accepting a proton. In accepting a proton, ammonia is acting like a Bronsted-Lowry base. The water, on the other hand, in this particular reaction, is donating a proton. We know it's donating a proton because when we look at H2O in the reactant and compare it to OH minus in the product, we see one less proton and more negatively charged by 1. Therefore, H2O donated a proton and is behaving like an acid. This is an illustration of an amphiprotic or an amphoteric substance. Now, water isn't the only amphiprotic or amphoteric substance, but all amphiprotic substances behave this way in that they can either accept or donate a proton. In talking about acid strength, we can evaluate different reactions, different titrations, or different forms of acid-base chemistry just by knowing strong acids and strong bases. There are very few strong acids and very few strong bases. So the key is to memorize the strong acids and memorize the strong bases, and all the other acids are weak, and all the other bases are weak. Acidic solutions are measured by the extent to which the acid reacts to put hydronium ions into solution. And so it's not the acid itself that makes a solution acidic or basic. It's how can the acid increase the concentration of hydronium ions, or H plus, in the solution. And the better an acid is at putting H plus into solution, the stronger that acid is, and the lower will be the pH. Strong acids ionize 100% in solution. It's important that you remember that. In other words, strong acids transfer 100% of their protons into the solution And that's why they're strong acids, because they're able to increase the concentration of H plus in the solution so greatly. That's why when we look at this generic reaction here, HA is our acid, reacting with H2O to form H3O plus and A minus, the conjugates of our starting materials, of our reactants. We see that we have an equilibrium that's very far to the right. In other words, 100% protons in solution means 100% ionization of this compound HA in the solution. So how much HA do we have? About 0% or very close to it when we put HA into water. The only thing we're seeing is H3O plus and H minus. We don't see any more HA in that solution. Or I should say we don't detect any more HA in that solution because we can't see it with the naked eye. So they say that the equilibrium of this reaction lies very far to the right. Weak acids, on the other hand, only partially ionize, less than 5%, in fact. So we say that the equilibrium lies very far to the left. And that's why this arrow that's pointing to the left is so much greater than the arrow on the top. We only have about or less than 5% ions, H3O plus and A minus, in this solution. And we have about, or maybe greater than, 95% of our original acid still in solution. Again, you need to memorize these acids. So put them on flashcards. We have hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, perchloric acid, and sulfuric acid. Those 6 commit to memory, and then everything else that you see that's acidic will be a weak acid. Get a little bit of a visual of what's going on in terms of the fact that we see an equilibrium that lies very far to the right. In other words, what we're going to see in solution are these ions that are in the products when we put a strong acid into water. So you see that if we have HCl in water, we drop that in, we don't see any more of that in the solution once we put it in. What we see, in fact, is hydronium ion and chloride ion, but no more HCl. That's because the HCl has completely ionized to H3O plus and Cl minus. In fact, this is a very strong electrolyte, as you learned when we were looking at electrolytes, because HCl will put H plus and Cl minus, 2 opposite charges, into solution. And it is those opposite charges that complete the circuit of 2 electrodes and lit up the light bulb that you saw in the demonstration last week. This is a 100% ionization, so this is a very strong electrolyte. And H3O plus is strongly acidic. So this solution, if we started out with a 0.1 molar solution of HCl, we would have 0.1 molar H3O plus in solution. We would also, of course, have 0.10 molar Cl minus in solution, but the Cl minus doesn't affect the acidity. It's only the H3O plus or the H plus that affects the acidity. If we look at weak acids, then the equilibrium is very far to the left. And if we put a weak acid like hydrofluoric acid, for example, which wasn't one of the 6 strong acids you're supposed to memorize, then we see that we still have plenty of hydrofluoric acid in this solution. We also have, of course, fluoride ion and hydronium ion, but not very much. And therefore, a weak acid is a weak electrolyte, which is something you learned about last week. I believe you had acetic acid that you looked at. which is another weak acid because it's not one of the 6 that you had to memorize. And so acetic acid is also a weak electrolyte. Again, less than 5% is ionized. So in fact, we have less than 5% of these ions in solution and greater than 95% of the original acid that we started with in solution. So if we started with a 0.10 molar hydrofluoric acid solution, we would not have 0.10 molar hydronium ion in that solution. It would be substantially less than that. Bases can also be categorized as strong or weak. They are measured typically in Bronsted, Lowry, and Arrhenius by how much OH minus they put into solution, or how many H plus can be attracted in solution. Strong bases attract large amounts of H plus. Strong bases will put large amounts of OH minus into solution. The strong bases for this course are going to be limited to hydroxides of group 1A and 2A. Now, there are other very strong bases that you'll talk about if you go further in chemistry, but for right now, we're going to talk about these 7. So the metals from group 1A form a compound with hydroxide, and these metals from group 2A form a compound with hydroxide. And these particular 7 are strong bases. So we have lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, and cesium hydroxide in group 2A metals, calcium hydroxide, strontium hydroxide, and barium hydroxide. Again, you need to commit these to memory. So get out the flashcards and put them on flashcards, because then any other bases that you run into will be weak. These bases, again, will ionize 100%, not unlike the strong acids. Weak bases are going to ionize, again, less than 5%. So a weak base that we could talk about is ammonia. Ammonia reacting in water is a weak base, so it's going to accept protons. In accepting a proton, you get ammonium ion. Here, water, of course, is acting like an acid. And as an acid, water is going to donate one of its protons. When it donates a proton, then what's left is OH minus, the conjugate base of water. The equilibrium of this reaction is very far to the left. In other words, we have a very small amount, some less than 5% ions in solution, and we have greater than 95% of the original base, NH3, which is a weak base, in solution. To get a visual on a strong base, we can look at sodium hydroxide. And so if we put sodium hydroxide into a solution, what you notice is that we no longer have sodium hydroxide here. In this solution, in fact, all we have is Na plus and OH minus. So if we had a 0.10 molar solution of sodium hydroxide, we would have 0.10 molar OH minus in solution. 100% is what we have of the ions here, which are products. Complete ionization. Sodium hydroxide is a strong electrolyte because it puts 100% Na plus and OH minus in solution, and that dipole will connect the circuit of 2 electrodes and light a light bulb. If we started out again with 0.10 molar sodium hydroxide, we would have 0.10 molar OH minus in solution, and OH minus is strongly basic. A weak base, on the other hand, is going to ionize less than 5%. So we're going to have less than 5% of these ions in solution when we put a weak base like NH3 in water. And you notice that we have still plenty of NH3 here in this solution. We have some OH minus and some ammonium ion in solution, but it's less than 5%. We have greater than 95% of the original ammonia still left in this solution. Ammonia is a weak base, and as you saw last week in the electrolyte demo, it's also a weak electrolyte. And that's if we have ammonia in water, because ammonia in water will release a small amount, less than 5% of ions. We want to have a quantitative way to analyze acid-base chemistry. So in addition to be able to look at it qualitatively and say, okay, we have a lot of ions in this solution because we have a strong acid or a strong base, or we have a minimal amount of ions in solution because we have a weak acid or a weak base. We want a quantitative number that tells us whether we have a strong acid or a strong base. And how strong is it? We want a quantitative number that tells us if we have a weak acid or a weak base, and how weak is it relative to another base. So we use the acid ionization constant, and you'll see that we also have a base ionization constant. The acid ionization constant is represented by this uppercase K and this lowercase a representing acid. If we look at a generic reaction where HA is our acid and water is acting like our base here, you notice that HA becomes A minus in the products, which means that it has one less proton, is more negatively charged by 1. And therefore, HA is an acid. On the other hand, water in this reaction goes from H2O to H3O plus and accepts a proton. So water is acting like our base. The way that we view a Ka then is by looking at how much ionization, because remember, if it's strong, then we'll have 100% ionization. If the acid is weak, we'll have less than 5% ionization. But the Ka can give us a quantitative value for that. So we look at ions, the concentration of ions on the top in the numerator of this ratio, and we look at the concentration of our original acid we started with in the denominator. That means that if we have a large Ka, we have a stronger acid because we'll have a larger number representing the concentration of the ions we have in solution, and a smaller value representing the concentration of the original acid we have in solution. This would make Ka large relatively, and that's a stronger acid. Notice that water is left out. And so the question is, why do we leave water out? You don't see it in the Ka expression. It would be here in the bottom, but again, we're leaving it out. And so why would we leave it out? Let me explain that these brackets that are around all of these different species represent molarity. So again, this is a measure of the concentration of the ions that we form in solution over the concentration of the original acid we started with when we put it into solution. Water, as you know, has a molar mass of 18.02 grams per mole. And at room temp, water has a density that's equal to 1.00 grams per mil. Now let's think about this. If we were to figure out the molarity of water, well, we do have in this calculation right here, moles, and we also have volume in mils, and those mils could be converted to liters, of course. And for molarity, the units are moles of solute per liter of solution. So could we figure out what the concentration is of water? And if we can, that means that water has a constant concentration at room temperature. So let's think about this. We need moles on the top. So we have 1 mole of water in 18.02 grams of water. And again, we're looking for concentration, so we want moles per liter. So we have 1.00 grams of water in the density in 1.00 mils of water. And again, we're looking for moles per liter, so we need to get rid of the mils and convert to liter. So in 1 mil, we have 1 times 10 to the minus 3 liters. And if we do this calculation, we notice that moles we still have, grams are gone, mils are gone, liters we still have. So let's do the calculation. And you get 55.49, and then this goes on and on, 389, and it keeps going. But ultimately, we're talking molarity here, which tells you water has a constant molarity. Now, if we're looking at Ka for some kind of a change as we go from reactants to products, and water always has a constant molarity, then we leave water out of this expression because it won't impact the changes in concentration that we have of our ions or of our original acid. Let's look at some Ka values and then also analyze why would we be interested in pKa values. So what is the draw to convert from Ka to pKa? Whenever you see a lowercase p in chemistry, that means you're taking the negative log of something, whatever it happens to be. So if you see pKa, then we're going to take the negative log of the Ka. And again, that lowercase p means negative log. No matter where you see it, that's what it's going to represent. Negative log of whatever you have. So let's start by looking at something like acetic acid. Acetic acid has a Ka of 1.76 times 10 to the minus 5. And then if we look at the Ka of something like nitric acid has a Ka of 27.79. If we have tables and tables of data with weak acids or weak bases, then we're going to be looking at a lot of data that has a lot of exponents that are highly negative. And it's much easier to look at a table of data that just has numerical values that don't have these huge or very small exponents associated with them. If we take the negative log, then, for example, of 1.76 times 10 to the minus 5, so we want the pKa. equals the negative log of 1.76 times 10 to the minus 5. And so in your calculator, you're going to put 1.76 EE 5 and then hit the plus minus key. And then you're going to hit your log key. And so what you get is that the pKa equals negative 4.75 4487, and this goes on pretty far, 332. Well, the negative of a negative is a positive, and so that means that the pKa equals 4.75. Now, if we look here, they're showing us a pKa of 4.76, a slightly different calculator than we used, or a little bit different numbers. Maybe they trailed past the 1.76 and we didn't, and that's why they got a little bit different number. If we do the same for the 27.79, then we get negative 1.44 for the pKa of nitric acid. Now, it's fairly easy to compare these two values. You can, without a doubt, determine that you have an increase in pKa as you go from nitric acid to acetic acid. So remember, we said that a strong acid is represented by a large Ka. But it looks like a strong acid is represented also by a small pKa relatively, because nitric acid is a strong acid. It's on the list of 6 strong acids that I told you to memorize, and acetic acid is a weak acid. So again, strong acids are represented by large Kas showing a large concentration of ions in solution. And if we take the negative log of that, then we get the opposite effect, where a strong acid is represented by a relatively smaller pKa. And a weak acid is represented by a relatively larger pKa. We also have ionization constants for bases, represented by the uppercase K and the lowercase b, b representing base. And this is an equilibrium constant for the reaction of a base and water, or we also call it an ionization constant, because again, it's going to be measuring the amount or the concentrations of the ions, that is the products ions, relative to what is the concentration of our starting material, our initial base. The more ions you have, the larger the numerator will be, and the larger the Kb is, and a larger Kb indicates a stronger base. We use the pH scale to quantitatively analyze acids and bases, or an acid-base solution in another way. So the pH scale is the measure of H+ in solution. Remember, we said that that P, that lowercase p, equals negative log. So if we want pH, that means we have the negative log of H. And in this case, with acids and bases, that's the negative log of H+, because we know that that's our hydrogen that's in solution. This pH scale makes things convenient because, again, our concentrations of H+ can have a lot of scientific notation that we have to evaluate. But if we have a pH scale, Then the numbers go from 0 to 14. Some very strong acids, like you just saw, nitric acid had a negative 1.44. So we can have some negative values associated with our acids if they're very, very acidic. But ultimately, on this 0 to 14 scale, neutral is a pH of 7. A pH less than 7 is acidic, and a pH greater than 7 is basic. These pH values, again, are the negative logs of the molar concentration of H plus in the solution. And mathematically, we see that we have the pH is equal to the negative log of H plus, or we could say the pH is equal to the negative log of H3O plus. These two species are exactly the same because we know that H plus is not all that stable. So it's going to react with the water in solution and form H3O plus. But those concentrations will be exactly the same 1-to-1. And so we consider H plus to be equivalent to H3O plus, and we usually call it proton or proton concentration. Again, the lowercase p means negative logarithm of. So if we had an H plus concentration of 1 raised to the power of minus x, then the pH would be the negative log of 1 times 10 raised to the power of minus x. And the pH equals x. Let's think about how that works exactly. And let's just look at an example. A real example. So let's turn x into 7, for instance, since 7 is neutral. So we have H plus equals 1 times 10 to the minus 7. And let's just look at what kind of a pH something like that would give us. Well, it says the pH equals the negative log of our H plus concentration, which is 1 times 10 to the minus 7 in this arbitrary case that we started. And so let's calculate the pH. If we input into our calculator 1EE7 and hit the plus minus key, and then hit the log key, and then we know we have to take the negative of that negative 7. So that means the pH is equal to 7. So that's interesting. It's a good shortcut because if, for example, we have a concentration of our H plus, then we know that our pH is going to be equal to that exponent, just like this is described here. But then on the other hand, if we don't have a coefficient of 1, then this won't hold. And by coefficient, I mean this species right here. That's the coefficient in the scientific notation, and that's a coefficient of 1. Suppose we change that coefficient to 5. So we would have that the pH equals the negative log of 5 times 10 to the minus 7. Now will we still get a pH of 7? So we input into the calculator 5EE7 minus, and then we hit the log key. And we know that because there's a negative log, we have to take the negative of the negative value that we have in the calculator. And so what we have for the pH is 6.3. We no longer have 7. And so we change that coefficient from 1 to 5, and this shortcut doesn't hold anymore. But just remember, you can always use that shortcut if your coefficient is 1. So if we use a log base 10 scale, which is what we're using to convert our hydrogen ion concentration to a pH. A log base 10 scale means that when we go from 7 pH to a pH of 10, that's not going to be 3. A log base 10 scale tells us that's going to be 10 raised to the power of 3. So if we go from pH 7 to pH 10, that's 1,000-fold difference in the H plus concentration that we have in that solution. If we go from a pH of 3 to a pH of 5, that's 2, but that's a log base 10 scale. So that is 10 times 10, or 10 raised to the power of 2, which is 100-fold difference in the H plus concentration. So now you can see why maybe people would die if you had a change in pH from 7.4 to 8.4, which is more basic, because that's actually a 10-fold difference in the concentration of H plus, which is putting someone in serious health conditions in their blood. Water is this special case, again, that we started this whole conversation about. And because water is so dominant in all of these acid-base chemistry reactions, water has its own ionization constant. And its ionization constant is Kw, and the W stands for water. So water has this reversible reaction that produces 1 OH minus and 1 H plus for every 1 molecule of water that we have. And water behaves very constant. So at room temperature, which is around 24, 25 degrees C, this H plus concentration is equal to this OH minus concentration, which is equal to 10 to the minus 7 molar. So H plus concentration is 10 to the minus 7 molar, and OH minus is 10 to the minus 7 molar. Now let's think about this reaction and how we would put together an expression for Kw. We would have the concentration of the ions in the product, and that would be over the concentration of our initial starting material, which is water. But if you remember, water is left out of these expressions because its concentration remains constant in these reactions. So that means that the equilibrium expression, or the ionization expression for water, is simply H plus concentration in molarity times OH minus concentration in molarity. And that's what we have right here. And so if the concentration of H plus at room temp is 1 times 10 to the minus 7, and the concentration of OH minus at room temp is 1 times 10 to the minus 7, that means that we do the math and we get 1 times 10 to the minus 14. And that equals Kw. So we have a constant that is equal to Kw that we can use when we do quantitative calculations that are associated with our concentration of OH minus that we have in solution versus our concentration of H plus. And because this is an inverse relationship, if H plus concentration increases by a factor of 10 because we add more acid to our solution at room temp, then the OH minus concentration is going to have to decrease by the same factor. Likewise, if we created a 10-fold increase in the OH minus because we added base to our solution at room temp, then the H plus concentration would have to decrease by the same factor. Again, because of this inverse relationship, and because of the fact that water is a constant, and this 1 times 10 to the minus 14 is always going to hold if you're at room temp. So remember from the previous slide that for pure water at 24, 25 degrees C, we're talking room temp, the H plus concentration and molarity is equal to the OH minus concentration and molarity, and they are both 1 times 10 to the minus 7 molar. So if we calculate Kw, that equals the concentration of H plus times the concentration of OH minus, and that is 1 times 10 to the minus 14. So for pure water at room temperature, the pH is equal to the negative log of 1 times 10 to the minus 7, and we calculated this a couple slides back, so that equals 7. The pOH is going to be equal to the negative log of 1 times 10 to the minus 7, which equals 7. So if we have the pOH plus the pH at room temperature, the pH is 7. The pOH is 7. 7 plus 7 equals 14. And now we have another relationship associated with pH and pOH that we can use to do quantitative calculations, provided 14 holds. And because water is constant, then 14 is going to hold. So if we have an increase in the pH, we have to have a decrease in the pOH, and vice versa, because their sum is always going to equal 14. So let's work out a couple of examples with these new methods of calculation that we can use for quantitative analysis of an acid-base solution. In this first line here, they give us the OH minus concentration. Now we know that the H plus concentration multiplied by the OH minus concentration is going to equal 1 times 10 to the minus 14. That is Kw for water, and that holds. So we can plug in what we have. And we have OH minus, which is 3.2 times 10 to the minus 3. And remember, these brackets equal molarity. And we set that equal to 1 times 10 to the minus 14. To solve this, we're going to divide 3.2 times 10 to the minus 3 out of both sides. It's going to cross cancel on the left. And we'll be left with H plus over there. So our H plus concentration, when we do the math, and that'll be 1 EE14 and hit the plus minus key, divided by 3.2 EE3 and hit the plus minus key, leaves us with 3.125 times 10 to the negative 12. And that is our concentration of H plus, our molar concentration of H plus. Now, we start out with 3.2, so we're going to have 2 digits here in our sig fig, so that puts us here. So it's actually 3.1 times 10 to the minus 12. And now to get the pH, all we need to do is take the negative log of 3.1 times 10 to the minus 12. So it's already in your calculator. You just hit your log key. And then, of course, a negative of a negative. So I'll just write this here so you have it. And again, I'm going to use all those digits when I calculate the pH, but when I report the H3O plus concentration, I'm going to report it with the correct number of significant figures, 3.1 times 10 to the minus 12. When I do this logarithmic calculation, I get 11.505 14998. for pH, and then I have to make some judgment calls about significant figures. And now significant figures is different with logarithms. So you can see I gave you a note down here at the bottom of the screen. The number of significant figures in the scientific notation are the coefficients. So we need to take note of that. And that is two values here and here, is equal to the number of digits to the right. Okay, sorry, folks. I don't know how I managed to do that. There we go. Okay, equal to the number of digits to the right of the decimal. I'm going to try it again. Place in the pH. So that means that we're going here to this 0. We evaluate the next digit over, and that's 5 or greater. So our pH is actually going to equal 11.51. I'm going to leave the other 3 for you to work out on your own later. You can also characterize acid, base, and neutral solutions by the concentration of H plus and OH minus in another qualitative way, by determining whether a solution is acidic, basic, or neutral because of the concentration of H plus or the concentration of OH minus. So if a solution has a greater concentration of H plus, then that solution is acidic. If a solution has a greater concentration of OH minus relative to H plus, then that solution is basic. If the solution has equimolar amounts of H plus and OH minus, that solution is neutral. An acid-base neutralization is generally accomplished with a titration. And we will talk about titrations. But let's look at the reaction first. And this AX reacting with BY to form BX and AY is a generic reaction. But what I want you to notice is that this particular acid-base reaction is also a double displacement reaction, where the positive cation A and the positive cation B are going to switch partners. So you see that A is with X in a compound in the reactants, but A is with Y in a compound in the products. B is with Y in a compound in the reactants, but B is with X in a compound in the products. And if we look at a real reaction between hydrogen chloride gas and sodium hydroxide, then the hydrogen and the sodium cations are going to trade partners. And what you see is that the hydrogen is now with the OH minus in the products. H2O is simply HOH, remember. And the sodium switched from the OH minus partner to the Cl minus partner in the products. In other words, when you start with an acid and a base, you end up with a salt and water in a neutralization reaction. The salt, sodium chloride, is neutral. And water has a pH around 7. It's also neutral. So we've neutralized this very strong acid and this very strong base. How do we know we have a strong acid and a strong base? So that we know we will form a salt and water in the products, because we memorized the 6 strong acids and the 7 strong bases from a few slides back. The neutralization occurs because the neutral salt is formed as a product containing the negative ion from the acid ionization. In other words, we had H plus and Cl minus in that acid, and now our salt in the product contains this negative ion Cl minus. And the positive ion from the base dissociation. In other words, our base was Na plus and OH minus, and so our product contains the OH minus and the positive ion from the base dissociation has teamed up with the negative ion from the acid ionization, giving us sodium chloride, a neutral salt. How do we balance acid-base neutralization equations? Well, we know that for every one H plus, one OH minus is going to team up to form H2O. Again, H2O is simply HOH. So our H plus and our OH minus come together to form neutral water. If we have HCl reacting with NaOH, we know that we have one H plus and one OH minus, which is going to form 1 mole of water. This is a monoprotic acid, and this is the way any monoprotic acid would balance, including HF, HBr, HI, reacting with sodium hydroxide. But if we have a diprotic acid, like sulfuric acid, there are 2 protons here. That means that we will need 2 OH minuses to form 2 moles of water in the products. And so we have to take into consideration if we have a diprotic acid, if we have a triprotic acid like phosphoric acid, which has 3 protons, we'd need 3 OH minuses to take care of that. Now to this, I'm just going to add the fact that we don't necessarily always have 1 OH minus. For example, if we had calcium hydroxide, there would be 2 OH minuses. That would change our stoichiometry if we had a monoprotic acid or a triprotic acid. We'd have to balance the equation correctly associated with that. Let's complete the missing data here. And so if you remember a few slides back, we said that the pH plus the pOH is equal to 14 because of the ionization of water always being constant. And they gave us a pH here of 2.33. Plus our pOH is going to equal 14 because the ionization of water is always constant. To solve this, we're going to subtract 2.33 from both sides. And over here, it's going to cross cancel. Then that's going to give us our pOH. So we have 14 minus 2.33, which is 11.67. And we're going to keep 11.67 because we have 2 significant figures to the right of the decimal in the pH, and we want to keep 2 significant figures to the right of the decimal in the pOH as well. And now we need to calculate H3O plus. So in calculating H3O plus, we need to do what's called an antilog. And so antilogs, because we had a log-based scale, so in other words, let's think about how we got the pH in the first place. The pH is equal to the negative log base 10 of the H plus concentration. Okay, so if pH is equal to negative log base 10 of the H plus concentration, that means that the pH is an exponent. That's what logs are. And we can also divide this -1 right here out of both sides. That means it would cancel over here on the right, but we would have a negative pH, which would give us a negative exponent of log base 10. So the way to solve this would be 10 raised to the value of the negative pH, whatever that happens to be. And your calculator has a built-in solution for antilogs. If you hit the second key, which is either green or yellow on your calculator, and the log key, you can see right above the log key, there's either a green or a yellow 10 raised to the power of x, and that's the antilog. So let's think about how we would do this. We're going to take our pH, because again, we're looking for H3O plus concentration. That comes from our pH, not our pOH. And we put in the exponent 2.33 and hit the plus minus key so that we get the negative exponent. Then we hit second log, and that gives us our concentration of H3O plus. Now, mine is in standard numerical notation, and I want it to be in scientific notation. So I'm going to hit second 5 to get it into scientific notation. Now I have that the H plus concentration, and again, I got this from this information right here. And I use the built-in antilog in my calculator. So the concentration of H3O plus, or I'm just going to write H plus to shorten it, is 4.677. 351413, and I'm just going to stop there, times 10 to the negative 3. And I stopped there because I know my significant figures are going to stop way before that. And now I need to make sure that I have the same significant figures in my coefficient that are to the right of the decimal in the pH. And that is 2. So that puts me here, this 4.6. When I evaluate the next value over, it's 5 or greater. So my H plus concentration is going to be 4.7 times 10 to the minus 3 molar. Okay, and I'm going to leave the other one for you to solve later. And here's another your turn that I'm going to leave for you to solve later, but I want you to realize they're asking you for pH, which is derived from the H3O plus or H plus concentration, and they give you the OH minus concentration. So this is a multi-step problem. And that brings us to talk about buffers. Buffers are interesting because this is an acid-base solution that resists changes to pH when you add strong acid or add strong base. And biological buffers are really important to maintain systems. We have phosphate buffers, we have carbonate buffers. They maintain systems at a certain pH because when you have proteins that are in a pH they're not accustomed to and that only needs to change by a small amount, half a pH value will make someone sick because their proteins will start to degrade. So OH minus and H plus ions are consumed by the buffer pair. And that means that the buffer will resist any changes because it's consuming the two ions that will either increase or decrease pH. A buffer system has a very important pair of partners, a weak acid and its weak conjugate base make up a buffer pair. So if we're looking at the mechanism of a buffer pair, again, here we have a weak acid and its weak conjugate base. So let's say, for example, that our weak acid is acetic acid. And the weak conjugate base then is going to be acetate. And we could put these two species in solution by starting with acetic acid, putting it in water, and we know that we would get the conjugate base of acetic acid, which is acetate, and H3O plus. So our question is, what happens if we add strong acid, or H plus, to this solution? Or alternatively, what happens if we add strong base or OH minus to this solution? Because we know if we had a strong acid like HCl, it would ionize 100%. It would put H plus and Cl minus in the solution. The Cl minus does not impact the acid-base chemistry, but the H plus does. If we put a strong base like sodium hydroxide into solution, then we would have Na plus and OH minus. The Na plus doesn't impact acid-base chemistry in any way, but the OH minus does. So those are the two ions that we're interested in here, and we need to remove them from solution as they're being added if we're going to resist changes in pH. So let's just look at the OH minus first. If we have OH minus and we start adding that to our solution, the question is, what is the OH minus going to do here? Which of these species is it going to react with? In other words, which member of our buffer pair is going to take the OH minus out of solution? And the fact is that the OH minus is going to react with this H plus in our conjugate acid, our weak conjugate acid. When it reacts with that H plus in our weak conjugate acid, it's going to form water, HOH or H2O. The other species that's going to be formed from this, so one thing we form is H2O because the OH minus reacts with the H plus in acetic acid. What's left over is the conjugate base of acetic acid, acetate. And so you ask yourself, how does this prevent a fluctuation in the pH? Or how does this resist a change in the pH? Well, water that's formed here is neutral. And acetate is a weak base. Being a weak base, it's only going to be reactive less than 5%. And so acetate is not going to change the pH that much. Very, very weak base. So we've resisted changes in pH this way. What about, on the other hand, if we added H plus? So if we add H plus to this system, in other words, we start adding a strong acid to this system, which one of our buffer pair is going to react to remove that H plus from solution? And it turns out that the one that's going to react with it is going to be our conjugate base of our buffer pair. It has a negative charge, and that H plus has a positive charge. They will attract one another, and what will we form? What will form is CH3 COOH, or more of our weak acid. Now, how does this prevent the pH from plummeting? Because that weak acid is only going to ionize an H plus less than 5%. So it's not going to put very much at all of this H plus back into solution. Once the conjugate base takes it, it sticks to the conjugate base at least 95% of the time, if not slightly more. So the conjugate base has removed the H plus from the solution. And this is the way a conjugate acid-base pair that are weak can remove OH minus or H plus from a solution and resist changes in pH. You should be able to draw all of this out on this slide yourself without listening to me prep you to understand it. Now, we said that this usually occurs in a titration. So let's have a look at how this is going to occur in a titration. And let's have a look at what it means for a titration to be reacting. If we had, so let's look at this, and we can see that it's telling us we have a weak acid and a strong base. We know that sodium hydroxide is a strong base because that's one of the strong bases we memorized. We know this is a weak acid, and here's why. When we evaluate our titration curve, our starting pH is here. That's over 2. If we had a strong acid, we would have a much lower pH starting out because the only thing that we're measuring is just the acid pH alone. When we start this reaction inside of this Erlenmeyer flask, the only thing we have is our acid, which in this case is HPR, a weak acid. And the other thing that we have is indicator, which in this case, our indicator is phenolphthalein. So we check the pH of our acid when we first start, and it happens to be above 2. We know then that this is a weak acid, even if we didn't know the identity of that acid. By looking at our titration curve, we would know that we had a weak acid based on that pH value. Notice that the weak acid forms this buffer region as soon as we start to add sodium hydroxide. So we add 10 mils of sodium hydroxide, 20 mils of sodium hydroxide, and we see this buffer region where we have resistance in the change of pH. So we're sitting at a pH that's around 4 to 6 and resisting any changes, even though we add 20, 30, 35. It's not until we add 40 mils of sodium hydroxide that we see this increase in the pH from a pH of about 4, 5, a pH of about 5, jumping up to a pH of over 10 all of a sudden when we add 40 mils. So what happened when we added 40 mils, or just over, a drop over 40 mils? Well, what's going on at the equivalence point is that we have equimolar amounts, equimolar concentrations or molarities, molar amounts of our strong base, or our base that we're titrating in here, and our original acid, in this case, HPR. We have equimolar amounts of those two species. Keep in mind what's happening here with this reaction. We have HPR reacting with NaOH. And it's a one-way reaction because we just keep adding sodium hydroxide. So we can only go in one direction. But we're going to get the conjugate base of our HPR, which is going to be PR minus. And it's going to be hanging around with the positively charged sodium. So let's just put that sodium there, even though the sodium really has nothing to do with the acid-base chemistry here. But we have this Na plus, which is going to hang around this PR minus, our conjugate. And then the other thing that we have is water, H2O or HOH, however you want to write it. But what's interesting is that what we're forming in this solution is a buffer pair. Here's our weak acid, and here is its weak conjugate base. So as soon as we start adding sodium hydroxide, we start forming a buffer pair in solution. And that's why we have this buffer region, because we're resisting changes in pH. And then we have 40 mils of 0.1000 molar HPR. Our concentration for NaOH is also 0.1000. So those are equal concentrations. And the HPR and the sodium hydroxide are 1-to-1. So once we add 40 mils of sodium hydroxide, we have equimolar amounts of HPR and OH in solution. And that's where we have our equivalence point. So the OH minus is equal to the HPR concentration right here at this equivalence point. So let's evaluate a little bit step by step these acids and bases. Acids release hydrogen ions, and the addition of acids is going to increase those hydrogen ions in solution. Increasing hydrogen ions decreases the pH because the solution becomes acidic. You add acid to a solution, the hydroxide ions are going to start combining with the H plus that you're adding to form water. And that's going to decrease the OH that you have in solution. Increasing H plus is associated with decreasing OH minus, according to KW. Bases combine with hydrogen ions. The addition of base reduces, therefore, the amount of hydrogen ion in a solution. Decreasing the H plus results in an increasing pH. So if you add base to a solution, the H plus decreases. And remember that if we decrease the H plus, we're going to increase the OH minus, according to the ionization of water and KW. An equation that will show this relationship between conjugate acids and bases is called the Henderson-Hasselbalch equation. It's derived from the expression for dissociation of a weak acid. And what it says is that the pH is equal to the pKa plus the log of the concentration of the conjugate base over the concentration of the conjugate acid. So this allows for a calculation of the pKa of a weak acid, or the calculation of pH, or we can also calculate the concentration of a weak acid and a weak base that we need to mix together to obtain a desired pH. And we use titration to do this. Let's look at a calculation associated with Henderson-Hasselbalch. And I know this equation looks nasty, but I'm not going to give you really hard calculations. The hardest kind of calculation I'm going to give you, you're seeing right now on the screen. So it's asking, what is the pH? So we're solving for pH here. This is what we're after. And it asks, what is the pH of a buffer solution that is 0.5 molar formic acid? And so that is 0.5 is representing our HA, and 1.0 molar in sodium formate. And so this is our base. .5 molar is our acid. And then we have 3.74, which is our pKa. So we just start plugging things in to this equation, and then we can solve. So the pH is equal to the pKa, which is 3.74, plus the log of A minus, our conjugate base, which is 1.0, over HA, our conjugate acid, which is 0.5. And again, this equation will only work for conjugate acid-base pairs. And when we do the math here, we have 1 divided by 0.5 equals, and then we hit the log key, and then we add 3.74. And we get 4.04, 102999, and it keeps going, but I'm going to cut it off there because I know that's way more sig figs than I need to worry about. And so I look at my value that I have for pKa, and I look at my values that I have for A minus and HA. This is the pH, so it's got to be reflected. by the concentration of the acid. The acid has one significant figure in it. So that means that I'm going to have one significant figure to the right of the decimal in my pH. I look at the next digit over, it's 4 or less. And so the pH here is going to equal 4.0. Now let's look at another titration curve and talk about what's going on here. And without even looking at any of the text, right away, we know that we have a weak acid because we can see that the pH is above 2. So we're titrating a weak acid with a strong base. We know NaOH is a strong base because we memorize the strong bases. We see that the equivalence point here is above 8, not unlike the last titration curve that we looked at. Now, in the video that you watch, you have a strong acid and a strong base neutralizing each other. So the equivalence point is at a pH of 7. But here, because we have a strong base, that skews the pH of the equivalence point to a higher value that is a little bit slightly more basic, 8.73. We know at the equivalence point, we have equimolar amounts of our acid, and here they're telling us it's HA. So we have equimolar amounts HA and we could say NaOH, but really it's OH minus, right? So we have equimolar amounts of our weak acid and hydroxide ion in solution at the equivalence point. Now, let's have a look at something else here. Let's have a look at half the equivalence point. And at half the equivalence point, you see that the pH equals the pKa. Now, how did that happen? Let's think about the Henderson-Hasselbalch equation that says pH equals pKa plus the log of the base over the acid. And that's conjugate base and acid. So, in other words, for the pH to equal the pKa, all of this has to equal 0. And the log of 1 is equal to 0. So the way that we get that to 0 out is we need for our A minus concentration to be equal to our HA concentration. At 1/2 the equivalence point, then, if the pH is equal to the pKa, our conjugate acid-base pair have to have equimolar amounts at that place. Now, again, thinking about how this works, if we have HA reacting with NaOH and we write out this reaction, HA reacting with NaOH, we know that what we're going to form is Na and then A, the conjugate base. So this is plus and this is minus. That's the conjugate base of HA plus water. So we're looking for the place where these two values, this concentration and this concentration, are equal, equimolar values. That's where our pH is going to equal our pKa. And when we get to 1/2 of whatever the equivalence point happens to be, and so the equivalence point is around here, and so 1/2 is around here, so that's approximately 25 mils of OH minus we've added, give or take a little bit. because the equivalence point occurs around 50. And so at this point right here, where we've added approximately 25 mils of OH, that's where we have 1/2 the equivalence point, and it is here that we have equimolar HA and A minus, the conjugate acid-base pair. So very different from the equimolar amount that we have, the equivalence point. The equivalence point is our weak acid concentration and our strong base concentration that were added. They are equimolar. But here, where the pH equals the pKa, according to Henderson-Hasselbalch, we have equimolar amounts of our conjugate acid-base pair. Let's look at a titration problem. And if we start by listing what we have in this problem, we know that we have 25.00 mils of sodium hydroxide. We know that the concentration of that sodium hydroxide is 0.300 molar. We have a dilute solution of sulfuric acid, and we neutralize during the titration with 37.5 mils of H2SO4. And we want to know what is the molarity or moles per liter of H2SO4. And we can just change that molarity to moles per liter just to remind ourselves of what we have. If we start evaluating here, we can see that we have mils, we have liters in our two known values. And here we have mils again. So we're going to have to work that out when we start looking at this problem. Now we do know, since we have volume and molarity, if we convert those mils of sodium hydroxide to liters, we can multiply that by the molarity of sodium hydroxide and get the moles of sodium hydroxide. But we have to go from sodium hydroxide to sulfuric acid. That is component A to component B. And the only way we can do that is with stoichiometric coefficients. So we need the balanced reaction equation here. So if we start with the balanced reaction equation, then we have H2SO4 reacting with NaOH. And that's going to give us a salt, which is going to be sodium sulfate, and water. But because this is a diprotic acid, we know right away that this reaction equation is not balanced. So we have two hydrogens going to have to react with two hydroxides to form two waters. And now our balanced equation, now our equation is totally balanced. So we can start working out this problem. We'll start out with our 25 mils of sodium hydroxide, which we know has to be converted to liters. And now we can use our sodium hydroxide molarity. So we have 0.300 moles. And again, that's NaOH. and that is in 1 liter of NaOH. And now our liters cross cancel. We have moles of NaOH, and so we can use our balanced reaction equation to go from moles of NaOH to moles of H2SO4. And when we look at the balanced reaction equation, we have 2 moles of sodium hydroxide to 1 mole of H2SO4. Now, what we're being asked for, though, is molarity of H2SO4. So we have moles of H2SO4, but we need moles per liter. So if we need moles per liter, then we have to divide our moles of H2SO4 by our volume of H2SO4. And up top, we see that we have mils of it. So we need to get rid of the mils and get to liters. And so in set up dimensional analysis, and we get 0.0375 liters of H2SO4. And now all we have to do is the math. And we get 0.1 molarity. And we know this is all multiplication and division, so we need to resolve our significant figures. This is 4 sig figs. This is 3 sig figs. And this is 3 sig figs. So our answer needs to have 3 significant figures. And so the H2SO4 concentration is equal to 0.100 molar. That wraps up our lecture on acids, bases, buffers, and pH.